Hi folks, my name is Robert. I'm the React Data team here at Meta, where I work on a framework called Relay. We released it a few years ago, and some of you have probably heard of it before. But look, it's come a long way in the past couple of years. It's time to take a fresh look. I think Relay should be considered for every React app that consumes GraphQL data because it does things that no other framework can do. It does crazy things to give your app a level of performance that isn't possible any other way. It gives your apps an unparalleled level of stability and makes large classes of bugs impossible. And it provides high-level tools for implementing the types of interactions that are present in every app, but whose details are really hard to get exactly right. Look, I'm going to talk about what Relay is, but I'm also going to dive into its internals. But bear with me here. It's all in the service of making those outlandish claims believable. And in the end, I've got some exciting news to share with you, so don't you go anywhere. So, what is Relay? Relay is a framework for building React apps that consume GraphQL data. It's in use throughout the Facebook web and mobile apps and across many internal tools. It's our go-to way of building data-driven JavaScript apps, and it's been around since 2015, so it's battle-tested, stable, and performant. Okay, but before we dive into Relay, let's take a step back and ask, why do I even need to use a framework to consume GraphQL data? Can't I just make a network call? Well, you could. Let's go through the thought process of somebody that builds an app using local component state for network data and see why it leads to Relay. You might start by having each component fetch its own data. Now, no need to look at this code closely. All that's important is that it's an attendee profile component comprising many subcomponents. Each of them fetch their own data. So, what happens when this component is rendered? Well, React will render the attendee profile container, which will make a network request and show a fallback. When that request completes, React will render the container and its 3 subcomponents, initiating more requests and showing 3 more loading indicators. As those complete in whatever random order, the content will pop in. Eventually, the full component will be rendered. Now, I think we can agree that that's a lot of loading states to show the user, even for such a simple component. And unfortunately, quite a few websites still behave like that. But there are 3 other more subtle reasons that it's not a good way to build this component. First, it's slow. The network requests occur in a series. Second, since every component is concerned only about touching its own data, some fields will be fetched multiple times. There's no deduplication. And third, the choice of what loading states to show is dictated by how you divided the attendee profile into subcomponents, not necessarily by what's best for the user. Okay, so that doesn't quite justify using a framework. Maybe we could have the attendee profile component fetch the data for all of its subcomponents. Okay, so we'll stop fetching the data in each component and instead write one big query that fetches the data for the entire page. Now we're getting somewhere. The data is fetched in one pass, there's one loading state. It's kind of a nice user experience. But now imagine that you haven't looked at this component for a few months, and it's gotten a lot more complicated. You get a ticket to stop using this or that field in some subcomponent. So you change the component and then go to the query declaration and prepare to stop selecting that field. But can you? Oh no. Not without checking whether every other component is using that data. And what about accidentally through something like json.stringify or object.keys? And what if somebody lands a change at the same time that starts to use that field? Now, you may think I'm being Chicken Little, but this is a big reason for application instability. The problem is that there's an implicit dependency between the query declaration and its subcomponents. So what can we do? Both approaches have trade-offs. On the one hand, combining all of the data dependencies into a single request results in better performance and a better user experience with fewer loading states. On the other hand, when every component fetched its own data, it was easy to reason about each component in isolation. Let's unpack that last statement. Where the request actually occurs is irrelevant, as long as the data somehow makes it to the component. What matters is that each component declares its data dependencies locally. So, is it possible to have each component declare its own data dependencies and a single query fetch all of the data for a given page? Well, that's what Relay gives us. Relay allows each component to specify its own data dependencies using a declarative syntax we developed here at Meta called GraphQL. Each component specifies what data it needs, but not how to get that data. Relay also has a compilation step, where on every file change, it stitches those components' data dependencies into a single query that can fetch the data for the entire page. Basically, instead of writing one big query yourself, each component writes just the fragment of the query that it uses. Then the compiler reads all of your JavaScript files and outputs the best query that you could have possibly written. So, what happens now when product requirements change? Well, notice that the attendee name is selected by multiple components, but only appears a single time in the generated query. So, even if it was removed from one fragment, it would still be fetched and the other components wouldn't break. So, in each component, you can safely remove unused fields. But what if another component isn't declaring that they use a field but are nonetheless accessing it, for example through json.stringify or object.keys? There's still a risk that the app could break. Well, Relay makes this impossible through what we call data masking. Child components don't get past the full network response. Instead, each component is passed what we call a fragment reference and reads just the data selected by its fragment, nothing more and nothing less. So that means that it's impossible for a component to even accidentally depend on the data selected by another component, because it will never see it. This means that every component can be reasoned about in isolation. This bears repeating, because it is the crucial reason why apps built with Relay are stable and scale to many developers touching the same code. With Relay, every component can be reasoned about in isolation. Changes to one component can't affect or break another. And this usually comes with a performance penalty, but because of the compilation step, Relay gives you the best of both worlds. You can reason locally and optimize globally. That's the key thing that makes Relay unique, and it's really something special. Everything else from here on out, it's an added bonus. But the advantage of this setup aren't just that Relay creates a query with deduplicated fields and makes your app more stable. Now remember, one of the disadvantages of the first approach was that what loading states we showed were dictated by how we divided the attendee profile into subcomponents, not by what was best for the user. Well, with this setup, we can avoid baking in decisions about where to show loading indicators, preserving flexibility. But before we discuss how we choose where to show loading states, let's talk about a situation where we wouldn't want a page-wide loading state. First, if a user is navigating from a list of attendees to an attendee profile, it would be nice if we could immediately reuse the data that we have to show the header of the attendee profile and show a fallback for the parts of the UI where we don't yet have data. Or second, imagine we're loading a page where there are some slow-to-calculate fields used by nested components. It would also be great to receive the quick-to-calculate parts of the query and to not have to wait until all of the data is received before we can render anything. Then we could render the outer components and show a fallback for the nested components that use the slow-to-calculate fields. Relay, working with React, makes this possible. It allows you to render the parts of the UI for which we have data, and then replace the rest with a fallback. The term we have for that is suspense for data fetching. This is a pattern in which components inform React that they aren't ready yet, but will be ready sometime in the future. In the meantime, React will render a fallback. Now, suspense for data fetching is a feature that was developed in close collaboration between the React and Relay teams. We had to substantially rework our initial suspense implementation, and we gave the React team valuable feedback that drove the development of suspense on their end. And right now, Relay is the first library to integrate with suspense for data fetching in a way that we're confident in. In fact, we've been using it on the Facebook web app for years and can stand behind it. It's stable, performant, and gives users great user experiences. But enough about suspense as a concept. Let's get down to how we'd actually achieve that behavior. The key thing to realize is that every component that reads data from the store can potentially suspend. A component might suspend if there isn't enough data to read out its fragment and there is a pending query that can provide that data. If a component suspends, React will go up the component tree to find the nearest suspense boundary. So, if a user navigates from a list of attendees to an attendee profile, we might have enough data to show the user profile container, but not have enough data to show any subcomponent. So it's the subcomponents here highlighted in green that might suspend. If the developer places a suspense boundary around the subcomponents, then when the user navigates, the container will be displayed, with a fallback replacing the subcomponents while the query is in flight. Notice that we made exactly no changes to the subcomponents. We just wrapped them in a suspense boundary. This is one of the key benefits of suspense. Components and loading states are separate concerns. Okay, but what about when a user loads a page for the first time? Is it possible to achieve this behavior? Well, by default, all of the data for a query is sent down in a single response, so the entire page will be rendered in a single pass. You'll never have a situation in which subcomponents suspend while the parent component does not. However, Relay provides an easy way to modify this behavior. Queries can be split into multiple responses using the defer directive. In effect, it instructs the server to send down the non-deferred data as soon as possible and to not wait until the deferred data is ready. We might choose to defer fragments containing the slow to calculate fields, for example. Now, if the deferred data is ready after the non-deferred data, it will be sent down a separate network response. So, this means that we can achieve the same behavior, showing outer components more quickly and showing subcomponents later, simply by adding this directive to our subcomponents fragment spreads. So, by adding defer and suspense boundaries, we can finally control the loading states that we show in order to provide the user experience that makes sense for our situation. And as a side note, the defer and stream directives were originally developed here in order to make our apps more performant and have since made it to the GraphQL spec. I think it's pretty cool. Now, being able to finally control loading states that are shown to users is great. But you and I both know that there's more to building a data-driven app than just fetching data initially. There are also common interactions, like refreshing data, refetching part of a query with different variables, or paginating a list. Relay has built-in support for these interactions. Let's go with pagination. Let's take a look at a list of attendees and add pagination to it. This is what the component looks like. Don't worry about reading the code. It just selects the first 4 attendees and renders them. But follow along as I add pagination. First, we add the connection directive to the list and give the refetch query a unique name. Next, we change the use fragment call to use pagination fragment, which gives us back data and load next. And now, let's hook up that load next to a button and render it. And next, I ran out of things to do, that's it. Clicking the returned button will load the next 10 items in the list. Adding pagination to a list with Relay is really that simple. Okay, so enough about loading states and how Relay helps you ship features quickly. Let's talk about consistency. This will highlight why Relay is so performant. If you update your profile photo in one part of the app, it's a bad experience if other components continue to show the old one. You can try to maintain consistency manually, but avoid our mistakes. Facebook tried for years to keep like counts consistent. It's not impossible, but it's hard, especially as the code changes. On the other hand, Relay and GraphQL were designed specifically to solve this problem. So, how does Relay do it? Relay keeps track of a flat or normalized store, meaning that all components that render the same entity ultimately access the same object, where 2 objects are the same if they happen to share the same ID. So, how would that work with a modified profile photo? Well, the component in the upper right corner of the screen might access that data by selecting me.profilephoto, and the attendee profile list might access that data through another path. But they're both accessing the same user object and thus the same profile photo. Now, if this user profile photo happens to change, then both components are re-rendered. In fact, only the components that read that data are actually re-rendered. So how does Relay do this? Well, when Relay reads out data for a component, it keeps track of the entities that component accessed. Then, whenever new data is written to the store, it compares the modified entities to the entities that each component accessed. If there's an overlap, Relay rereads the component's data. And finally, only if the read out data is actually different do we re-render that component. That's how, even in situations where there are many components on the screen, apps that use Relay can stay snappy and responsive. This can happen, for example, when a user scrolls a newsfeed-like UI. After they scroll down several pages, there can be many components rendered on the screen at once. And it'd be a pretty bad user experience if the app became more and more sluggish as users scrolled. Fortunately for you, we care deeply about the performance of the newsfeed, for obvious reasons, and we've spent a lot of time optimizing this exact circumstance. Now, This isn't the only way that Relay maintains runtime performance. The compiler also generates instructions for efficiently writing the results of each query back to the store. This is a crazy idea, so let me explain what's happening. Instead of looking at what fields are present in the network response and figuring out what to do dynamically, the compiler takes advantage of the fact that it knows what data will be returned and creates an extremely efficient data structure encoding exactly what needs to happen to write the network data to the store in practice. This data structure is JIT optimized. Like, we spent a lot of time thinking about how to make this extremely fast. Then at runtime, when we receive this data, we just zip through the data structure. And it turns out it's really, really fast. These instruction sets vastly decrease the amount of work we do at runtime. And according to some metrics, when we rolled this out, these instruction sets led to a 10x improvement in the time it took to write network data to the store. Okay, so we've talked about Relay scaling. It scales to the number of developers touching the same code base, it scales to the number of components rendered on the screen at once, and it scales in how large queries can be. But one thing we had trouble with was scaling how many queries we could handle in our code base. Unfortunately, GraphQL isn't very modular, so the performance of our compile step deteriorated as more and more queries were added to our code base. We saw the writing on the wall. We could eke out incremental gains in the performance of our compiler, but we needed something bigger. So, after some soul searching, we undertook a multi-year effort to rewrite the compiler in Rust. Rust is a great fit for our compiler, primarily because it lets us share extremely large data structures across threads safely and allows us to safely parallelize a lot of the work. The initial results were great. The new compiler improved performance by nearly 5x on average and 7x at P95. And those were just the numbers from the initial rollout, comparing the highly optimized JavaScript compiler to the fresh Rust one. We've continued to improve upon its performance since then. Some builds, which took over 5 minutes at P99, now have a P99 of about 30 seconds. Incremental builds often finish within hundreds of milliseconds. By the way, we have an absolutely massive number of queries in our code base, so if we made it usable for us, it's going to be lightning fast in most other code bases. And so I'm very excited to announce that just this morning, we officially released the Rust compiler to open source. The compiler is not only faster and more stable, it's also chock full of new features that help improve developer productivity. For example, it's a best practice to make fields in the schema universally nullable, since resolvers can fail for any reason without causing the entire request to fail. This causes a lot of null checking. I mean, don't look at this component closely, just look how much boilerplate there is. The new compiler ships with an @required directive, which will nullify the parent object or throw an error if the required field isn't present. Using this directive, application developers can curtail or eliminate null checks in their codebase, before and after. Look at that. That's 3 lines where there used to be 5 or 6. This may sound like a trivial quality of life improvement, but if half of your component is null checks, this is a pretty big deal. And the numbers don't lie. Developers love it. This directive has been adopted at an astonishing pace. Look, I'm coming up on time and there's a lot more that I wanted to cover. I didn't talk about how you can use preloaded queries to fetch data for components that haven't even rendered, so that when they do render, you can show them instantly. I didn't talk about how the compiler generates types for each query and fragment, catching many errors before the code even leaves your IDE. I didn't have time to talk about how Relay lets you write optimistic responses, making mutations seem instant to the user. But I do have time to tell you that Relay only gets better the more you learn about it. Speaking of which, earlier this year, we put a lot of effort into updating our documentation. We still have a ways to go, but it's much better than it used to be. So go! Head over to relay.dev, pause the stream, try it out. On the front page, there's a sandbox where you can begin playing with Relay. No need for an npm install. Thanks. Thanks for taking the time from your busy day to learn about Relay. Have a good one.